Welcome to The Explainer. All right, today we're going to tackle something that trips up a lot of people in differential equations. What on earth do you do when your problem has non-homogeneous boundary conditions? If you've ever just hit a total wall with a problem because it doesn't fit that perfect textbook example, well, we're about to break down a really clever technique to get right past it. So let's jump in. So, you're probably pretty comfortable with solving the heat equation by now. I'm sure you've used the separation of variables method a ton, and it works great, right? As long as the ends of your rod or whatever you're dealing with are held at a nice clean temperature of 0. But let's be honest, the real world is almost never that simple. And this is the question that changes everything. What happens if one end is cranked up to 100 degrees? Or, what if one's at 10 and the other's at 30? All of a sudden, our go-to method, separation of variables, it doesn't work. But why? Why does it fail? Well, it all comes down to the foundation that the method is built on, something called homogeneous boundary conditions. And that is just a fancy term for saying the values at the boundaries, the ends of our rod, have to be 0. This is the simple case, right? It's the one we all learn first, and it's absolutely essential for the math to play out correctly. And here's the real reason why. Separation of variables works by building your final solution out of a bunch of simple sine waves. And what do sine waves do? They naturally start and end at 0. So when your boundaries are not 0, you're basically trying to build something with pieces that just don't fit. The whole mathematical machine just grinds to a halt. It's a complete roadblock, so we need a new plan. We need a clever workaround. And that workaround is what I like to call the steady plus transient trick. And trust me, it is an incredibly elegant, almost beautiful way to get around this problem. We're not going to solve one hard problem. Instead, we're going to solve two way simpler ones. So here's the big idea in a nutshell. We take our complicated temperature problem, u of x, t, and we literally just split it. We decompose it into two separate components that we can then add back together to get our final answer. And each of these components has a very specific job. This equation right here, this is the heart of the entire method. Our total solution, u of xt, is just the sum of some function v of x and another function w of xt. Now notice the difference here. It's super important. V only depends on position x, while w depends on both position and time. That's the key. Let's see what each part actually does. Let's break down this team. First up, you have v of x. We call this the steady state. Think of it as the final, boring, stable temperature after everything is settled down. Its main job? To deal with those annoying non-zero boundary conditions for us. It takes the hit. Then you have w of xt, the transient part. This is the action. This is the dynamic part that changes and decays over time. And here's the clever bit. By design, we make sure it has those nice, simple, zero boundary conditions, which means we can solve for it using our old friend, separation of variables. So here's the 4-step recipe. It's really straightforward. First, you just state the decomposition. Second, you find the steady state, v of x. This part is usually super easy. It's often just finding the equation of a line. Third, you adjust the initial condition for your transient part. Since the total initial condition is just v plus w, w's initial condition is just the original one minus the steady state you just found. And finally, step 4, you solve for w of xt, which is now a totally standard homogeneous problem. Add v and w back together at the end, and boom, you've got your answer. Okay, that's enough theory. Let's make this real. Seeing this method actually work is the best way to understand just how slick and powerful it really is. Okay, let's start with a classic. Imagine you've got a rod that's 10 units long. The left end is held at a constant 10 degrees, and the right end is at a constant 30 degrees. So our very first task is to find the steady state part of the solution, that v of x. And this just shows how simple the steady state part can be. I mean, think about it. After a super long time, what's the temperature going to look like? It's just going to be a straight line connecting the two endpoints, right? So we just need to find the equation of the line that passes through the points 0, 10, and 10, 30. That's just basic algebra. And it gives us our steady state solution. V of x is 2x plus 10. Part 1, done. All right, let's try a different flavor of boundary condition, one you're going to see all the time in physics and engineering problems. This time, the left end is held at 20 degrees, but the right end is insulated. Now, what does that mean, insulated? In math terms, it just means the rate of change of temperature, the derivative, u prime, is 0. No heat can get in or out. So, how does that change our steady state, v of x? Well, we know v still has to be a line, ax plus b, because its second derivative is 0. The condition at x equals 0 tells us that b is 20, but the insulated end, the part where the derivative is 0, means the slope, a, has to be 0. So what's left? The steady state is just a constant temperature, v of x equals 20. And that makes total physical sense, right? If you hold one end at 20 degrees and block any heat from escaping the other, eventually the whole rod is just going to settle at 20 degrees. Okay, so now that we see how to find the steady state, let's get to my favorite part. This is the intuition, the mental picture that makes this whole thing just click into place. I absolutely love this quote from the source material. It is the single best mental model for this entire process. Just think about it. The solution is just a sine wave that rides on top of a line. So what does that actually mean? It means you should picture that straight, steady state line we found. Like v of x equals 2x plus 10. That's the backbone. That's the permanent part of the solution. Then you imagine that wavy, transient solution w of xt getting added right on top of it. And as time goes on, the height of those waves just shrinks and shrinks down to 0 until all that's left is that permanent steady state line. The transient solution is literally riding the steady state down to equilibrium. It's a great visual. So to wrap it all up, what are the big things to remember? Number 1, do not fear non-homogeneous boundary conditions. They're not that bad. The trick is to just split the problem in two. Let the simple steady state function, v of x, take care of all the messy boundary stuff. That leaves you with a standard, easy problem for the transient part, w of xt, which you already know exactly how to solve. And always, always keep that picture in your head, a decaying wave riding on a simple line. And that brings us to the end. I'm just going to leave you with one last thought. This idea of decomposition, of taking one really hard problem and breaking it into two easy ones, that's not just a trick for this one equation. It is one of the most powerful strategies in all of science and engineering. So think about it. Where else have you seen this used? Thanks for tuning in.